can also be used in digital logic circuits and to perform various logic functions. Okay, so they can be employed, used for logic gates. Okay, I mean the various gate circuits are always are usually transistor logic circuits. Okay, so for example, if you consider this inverter configuration of NMOS, two NMOS transistors, M1 and M2. Okay, both are NMOS transistors, and both are in inverter configuration. Okay, so there is a load that is attached. And practically, what happens is that when you have a TTL or transistor logic fabrication, this RD is replaced by a MOSFET transistor as well. Okay, you can have a load enhancement device. So this is also an enhancement MOSFET device over here. So everything is transistor based. Okay, so this is a two input logic gate, and the configuration is as such that we have two inverter circuits. Okay, two inverter M1 M2 NMOS transistors which are performing a certain logic function. So let's determine what this logic function is. Now, to understand this, you see for the transistor inverter circuit, you understand when the input is low. Okay, when the input is low, approximately 0 volts, then both the transistors are in cutoff. So that means the output voltage is high and becomes equal to VDD. So you see, if both the input voltages are less than, let's say, threshold voltage is VTN1, that is threshold voltage for M1, and then this is less than VTN2, then both the transistors are in cutoff. When they're in cutoff, there's no current. Okay, you don't have any ID1 or ID2 current. For this condition, okay, ID1 is equal to ID2, which is equal to 0. So that means you have an open circuits over here. The transistors are open. The transistors are open over here. So that also implies that your current IR, which is the summation of two currents. Okay, since this is bifurcating itself into IR bifurcates itself into ID1 and then into ID2. So well, these all currents are 0. Okay, that means the output can be seen from the circuit when IR is 0, and this current is 0. Then your output is high, which is equal to VDD or 5 volts. Okay. So for no input, the output is high. When there is no input at the two inputs of the gate, the output is high. Okay, so that's one. But when the input is high and equal to VDD, the transistor is biased in the non-sat region, so the output reaches to a low value. Now, since the input voltage will either be high or low, we can analyze the circuit in terms of DC parameters. So you see what happens is that well, if you have now if you have V1 greater than VDN, okay, now it is greater than VDN, it is greater than VDN. So let's consider a situation. Okay, let's keep the V2 less than VDN. So let's keep M2 in cutoff. Okay, so right now M2 is off. Let's apply an input such that M2 is off, but M1 is on. In order to turn this M1 on, V1, the input voltage or the gate voltage of M1 should be at least the threshold voltage, should be higher than the threshold voltage. This in turn lets the transistor operate in either saturation region or non-sat region. So if the high input, let's consider the high input as VDD, okay, either it is 0 or it is 5 volts. So if V1 is greater than VTN, and let's say this is V1 is equal to VDD, okay, then what happens is that your inversion layer, it creates the inversion layer, so your space charge density increases. This requires a large current ID1. So ID1 increases, basically ID1 increases. As ID1 increases, since there is no ID2, then in this case your ID1 is basically equal to IR, okay, and then since your ID1 increases, IR also increases. That means the output V0, which is given as VDD minus IR RD, this drop IR RD increases. Okay, this drop increases because both the currents are increasing. So when this drop is increasing, the output decreases. The output V naught decreases. So you see, for if the input is high over here, the transistor is on, the transistor is off, or M2 is off. So one is high, the other is low. You're going to basically what happens is you're going to bias this M1 in non-sat region, okay, because the output is low, okay, the output is low. So you're less than the VDS that you're going to get is less than VDS sat, because because of the current. You see, if the input voltage goes on increasing, okay, then that means the IR in this configuration, okay, the series current, drain to source current increases. Okay, this is your drain to source current increases. When drain to source current increases, then this voltage drop also increases. The voltage drop across load increases. So VDD minus IDRD minus IRRD, this drop increases, so V naught decreases. That means if any of the transistor is on and the other is off, it's the same scenario. The output is low. Okay, the output is still low. So you see over here, you consider the case when the second transistor is connected in parallel, which is shown in figure 46. Now, okay, we have talked about this. If the two inputs are 0, both are cut off, and V naught is 5. Well, okay, that's easy to see. When V1 is 5 and V2 is 0, the transistor M1 turns on, M2 is still off. But transistor M1 is biased in non-sat region. Why is it biased in non-sat region? Because the VDS is decreasing. You see, VDS in this case is your V naught. Okay, VDS across M1 is V naught. So VDS is decreasing on the IV characteristics. Although initially your VDS could be in sat region, but now it goes on decreasing as your input voltage is increasing. So you might turn your transistor operation into, I mean, you might get your transistor to operate in non-sat region instead of saturation region, because VDS is decreasing. This axis is VDS, and this is ID. The vertical axis is ID. That's the basic idea behind the inverter circuit. Okay, so if any of the two transistors is on, the other is off, the scenario is same. The output voltage is low. Okay, but when both are off, the output is high. Okay, so if V1 is 0, V2 is 5 volts, M1 is cut off, M2 is biased in non-sat region. Again, when V naught is at a low value, so if both inputs are high, then both the transistors are biased in non-sat, and V naught is again low. You see, the thing is, now if this is also turned on, so V2, let's say that V2 is also VDD. V2 is also VDD. And let's remove this. Okay, don't bother about VDN. Your inputs are high. V1 is VDD, V2 is VDD. That's 5 volts. Now what happens in this case is that the current requirement increases. The current requirement increases because the gate voltage is increasing. So physically, the inversion layer increases. The width of that inversion layer increases, which increases the space charge density. So drain to source current has to increase. And this has to increase. Both ID1, ID2 increases. This in turn increases your current IR1. So this has to increase. If this has to increase, then this drop IR RD further drops. I mean, the drop further increases. So with this increase, VDD is fixed. V naught is going to drop more. Okay, so even both the transistors are on, the output is low. Okay, so the idea is that if you can summarize this in a table, when the both transistors are off, the output is high. Okay, when either one is on, V1 or V2, M1, M2, the output is low. But when both are on, the output is again low. This is a classical example of what happens in a NOR logic function. So NOR, or you can say the opposite of what an OR logic function, OR logic gate does. Okay. So this table shows these various conditions for the circuit as we have discussed. So in a positive logic system, These results indicate that the circuit performs a NOR logic function, and it is therefore called a two-input NOR logic circuit. So in actual NMOS logic circuits, the resistor RD is replaced by an actual NMOS transistor. I mean, this RD could be an enhancement NMOS load device. Okay, we have talked about this where the gate and the drain are tied together. I mean, you can have a configuration like this for them. So this is your the gate can be tied to the drain. The drain is your clamp to call it VDD. This is a nonlinear resistor. I mean, instead of RD, you can have this configuration instead of RD over here. No resistor, no physical resistor. This is also MOSFET. This is an enhancement load device. Okay, so which has a nonlinear IV characteristics group above threshold, something like this. So this is your the idea is okay. We have to repeat that. This is your VDS, okay, and over here this is your ID. So in this circuit configuration, your VG is basically equal to VD. Okay, that means if the transistor is to be in enhancement load devices, the transistor operates in saturation region. So ID for NMOS device is given by Kn. Instead of VGS, I can write this as VDS minus VTN whole squared. So this is a curve, a quadratic curve in VDS, because VTN is fixed. That's like this point is your VTN, because you cannot turn on the transistor below VTN. After VTN, the conduction starts, the transistor turns on, and the current increases in a quadratic manner with regards to VDS, right? So this is a nonlinear resistor. You see, this IV characteristics, the gradient, the inverse of this gradient is your resistance. So you can have an NMOS device in place of an RD over here. So everything is based on NMOS. So in actual logic circuits, the resistor RD is replaced by another NMOS transistor. So everything is NMOS MOSFET based. So this is a classic example of a two-input NMOS NOR logic gate. Okay, so MOSFETs can also be used apart from being used as a small signal amplifiers, small signal time varying, amplifying the small signal time varying signals. They're also used as a logic gates, okay, in digital logic circuits to perform different Boolean operations. Now, this is example 3.13 from your course text. The objective is to carry out the DC analysis to further understand the operation of a NOR logic function in terms of the IV characteristics of MOSFET. So the objective is to determine the current and voltages in a digital logic gate for various input conditions. So you consider the circuit shown in the figure, right? This is the figures. This is the NOR logic function we have discussed before. And the circuit parameters are RD is given as 20 Ks. Okay, this RD is 20 kilo ohms, and your conduction parameter is given, which is 0.1 milliamps volt square. Then you have your threshold voltage for each transistor, M1, M2 as 0.8 volts. The channel width modulation parameter is set to 0, right? So that means you can consider M1 and M2 to be ideal. These are ideal transistors. So you don't need to consider forward resistance. In saturation, it's a plateau region. ID is constant. Okay. If lambda was not 0, then we have to consider some rise of the current ID. So that means ID is also dependent on VDS. That means the channel width is being modulated by VDS, or in other words, VDS is controlling the current ID. Okay, but this is the ideal. The solid ion is the ideal MOSFET. So if lambda is 0, you can consider the ideal IV characteristic for a MOSFET. All right. So in the first case, when V1, V2 are 0, when V1, V2 is 0, the transistor is in cutoff. That means IR is 0. Okay. Transistor is in cutoff. So V0 is VDD. So for IR is 0. So let me put this again. This is VDD minus IR RD. This is equal to V0 okay, output voltage. So when this thing is 0, then your output voltage is VDD, it's high, so it's 5 volts. So for V1 equal to 5 volts, V2 equal to 0, that means this transistor is on. 5 volts is also greater than the threshold voltage, 0.8 volts, okay. It's large enough to turn on the transistor V1. V2 is still off, okay. V2 is still off. So what happens in this case is that you, in order to evaluate the current, the value for the current in terms of RD and VDD, you consider the characteristic of the transistor IV characteristics in non-sat region. This is transistor characteristics, ideal transistor characteristics in non-sat region. Okay, the reason why, okay, it is on, it could be in saturation or non-sat. So it is in non-sat because your VDS is decreasing. I mean, even if you're applying a high input voltage like VDD 5 volts, this causes the current to increase, and when the current increases, your output voltage decreases. So basically the output voltage is VDS, so the VDS over here decreases. VDS decreases, you shift your transistor operation to from sat region to non-sat region. So transistor M1 is biased in a non-sat region. So that's why we are using this equation for non-sat IV. So my IR, because this is an open circuit, this is off, so you don't have any ID, you don't have any ID. So IR is basically ID1, which can be written as 5, okay, this is 5 minus V naught over RD, this is your IR, okay, which is equal to ID1, so that can be related to the output voltage in a quadratic manner in non-sat equation, IV equation for the ideal MOSFET. Solving this for V naught, we obtain V naught as 0.29 volts. Then you plug this V naught back in the equation for the current, and you find ID1 and IR at 0.3236 milliamps. Okay, so this is your Q point. I mean, this is where the transistor M1 is biased, and this is non-sat. So if you're going to reverse the roles, such that V1 is off and V2 is on, okay, vice versa, the situation is the same. In that case, ID2 will be 0.236 amps. I mean, you will have ID2 and you won't have ID1, but the analysis is the same for the same RD, okay, and same VDD. So your output is still 0.29 volts and the current is 0.236. But what happens when you turn both the transistors on? When both transistors are on, you see V1, V2 is 5 volts. Then you have to consider two non-sat currents, add them up, because these currents are your ID1 plus ID2, and this is precisely equal to IR. This is equal to IR. Okay, and IR is VDD minus V naught over RD, which can be solved again. It's a quadratic in V naught, so you solve it for V naught such that V naught is not in the saturation region, it's non-sat, so it's a small value, and this gives IR as 0.243 milliamps. Okay, and since both transistors are in non-sat and are non-sat, and both are, due to the symmetry of the circuit, you can see this ID1 and ID2, they are equal, so the current bifurcates itself into two equal parts, which means your ID1 and ID2 is the half of IR, 0.121 milliamps. So you see, when the transistor is biased on, it is biased in the non-sat region in this configuration because VDS is less than VDS sat. Okay, so the output voltage reaches a low state. Okay, this equation is defining why the transistor is in non-sat. Okay, because when your input is high, then the current is high. It's not zero. The current is high. So when the current is high, the drop increases. This drop increases, and therefore the V naught decreases. So VDS decreases. So VDS is somewhere here. This is non-sat. So that's why we are using this non-sat currents, okay, non-sat IV relationships to find the currents. So this example illustrates and discusses that the MOS transistors can be configured in a circuit to perform logic functions. And most logic gate circuits are fabricated using CMOS technology, which means designing the circuits require both N-channel, P-channel transistors and no resistors. Okay, so you might want to consider in the analysis, the more practical analysis, and not an ideal resistor, but a non-linear resistor that can be modeled or that can be fabricated through an NMOS transistor. Okay,